Hi, in this video, we're going to talk about single area OSPF. Excuse me. Actually, you're going to do more than talk about it. You're going to configure it. Okay, so here's the packet tracer topology that we've started up with. Here is the lab. So I'm showing the lab in a Word doc format. And I am in view, this, if you want to do it this way, view, and I have the navigation pane checked, and I've got the little document map here. Anyway, it shows you all the steps along the left here. And we are going to be going, I am going to be going through this lab, and you'll be following along using the lab itself. So for a few things first, let me kind of move this out of the way, and I'm going to talk about a few things that are all in this lab. First things I want to talk about is this here. This blue part of the network, this is where MOI Enterprises, this is the area in tan here that we're going to be configuring OSPF for. The edge router is then connected to the ISP, but also has this public part of its network. We're not going to configure this. Also, you're going to see there's some public IP addresses here with network address translation addresses here. We're not going to be using that as well. I actually use this in a later lab. So depending on what you're watching this video for, you may or may not be doing those parts later. Excuse me. The other thing I want to mention is that all these three routers, LAN 1, LAN 2, and Edge, actually and ISP, they do have some pre-configs. So they all have, enable secret class. So remember that. Also, the console password is Cisco. So Cisco and then class. You should be familiar with those commands. No IP domain lookup. The addressing has all been configured, and they're in the up and up state. Let's see, you'll see some line console stuff there, so it doesn't time you out of the console, logging synchronous, things like that. Okay, so you can see that addressing and the pre-configs for all the routers, including the ISP. Okay, no routing has been configured. Now, I did do something that I will be talking about, and again, depending on the class that you're in, talking about this here, spanning tree port fast. So what I've done on switch 4 here. So normally when you connect an end device or any device to an Ethernet switch, a router, a host computer, an end device, or another switch, it's going to run spanning tree. Well, spanning tree is always running, but what spanning tree is going to do is actually put that port in the switch port in various states. You'll see an amber light, even in packet tracer, and it takes about 50 seconds before it will start forwarding. It's to make sure that there's not another switch attached, and if there is, that there's not a loop that has been formed. Okay, well, what this command here does that I've already done for us on this switch is as soon as there's a connection to that switch port, any of the switch ports, it automatically goes into forwarding state. I know we do not have any switches attached, so I'm not worried about any loops, and this is going to make conversions happen much quicker. Talk about that again later if you're in a class of mine that we talk about a little bit about spanning tree. Okay, so I'm going to be going through this lab part by part. So now we're on part 0 still. But we're going to be, I'm going to be going through all of this. So it's all done for you in the lab. So let's take a look. I'm going to move that out of the way. And I'm going to bring up PC0 here. Open that up. I'm going to go to the desktop, command prompt. I'm going to do IP config. And what we are looking at here on PC0 is that it has a IP address subnet mask and a default gateway. The default gateway is LAN 1's gigabit 00 interface. All right, so what I've done here already for us, get that out of the way, is I have the 3 routers already up. By the way, here's LAN 1, LAN 2, and edge. I've already added the password Cisco when it prompted me here, and here I gave it the to go from user mode to privilege exec mode, the password class. All right, what I'm going to do here is just do show IP route. I'm going to take a look at the routing table. Whoops, got to spell route correctly. Always like making errors because it shows, you can always tell what is that error telling me. Did not understand this input right there. All right, so it says, hey, I have 3 directly connected networks. This is because I configured IP addresses on those 3 networks. And here's the 3 interfaces, or on those 3 interfaces, I should say. So I configured 3 IP addresses for 3 different networks on those 3 different interfaces. So it knows it's directly connected to those networks. Once again, no routing's been configured. All right, so if I am, let's go back to PC0 here. PC0 should be able to ping its default gateway because they are on the same network. Yes, and that works fine. Can PC0, however, ping PC1? This as a, learning to become a network engineer, it's important to understand what the network situation is so we understand what it can do and what it can't do. Okay, so let's think about this. I'm going to try and ping 10.02.100 PC1. Now, we just saw that router LAN 1 only knows about its directly connected networks. Okay, does not know about this remote network. So the packet should reach its default gateway from PC0 going to this destination IP address. But as we saw with LAN 1, it does not know where this network is, so it should drop the packet. And that is indeed what is happening. All right. So one of the things I'm going to do first here in the lab is on the ISP router, I'm actually going to configure. So let's go to the ISP router. Not going to do too much on the ISP. This is pretty much it. Oops, Cisco, enable, class. There we go. All right. So what I'm going to do on the ISP router is I'm going to configure a static default route. So let's do that, IP route. And what network am I trying to reach? I want a static route for the entire 10 network. I don't care if you're subnetted or not, Moy enterprises, just anything beginning with a 10 belongs to you. Now, normally this would be a public IP address, but we're not doing that here. Okay, we're ignoring any kind of public IP addresses. We'll pretend this is public for now. Okay, so I'm going to put 255.0.0.0 as my mask. Means the only thing that has to match is these first 8 bits, which is 10 in decimal. And anytime ISP receives a packet beginning with 10 as the destination IP address, it's going to send it to the next hop router, 172.16.1.1, which is edge router right here. So it's going to send, ISP is going to send it to edge and say, this is your responsibility from here on out. Okay, you take care of it. I just got it to you. You deal with it. All right. So, by the way, if I exit here and do show IP route, I will see that now I have this static route in the ISP's IP routing table. Okay, so does this mean now that ISP should be able to ping PC0? Well, let's take a look. Ping 10.0.1.50. We haven't done anything for routing here, right? So, as we can see, these pings are unsuccessful, unreachable. Well, basically what's happening is ISP says, I'm sending the pack anything for this network, this packet to this network, I'm sending it to 172.16.1. So it's reaching edge. Okay. The thing is, does edge know how to get to the 10.0.1.0 network? Well, as we've seen previously, well, let's take a look. Let's do show IP route here. It only knows about its directly connected networks. Just like LAN 1 and LAN 2, edge only knows about this network and this network. That's it. Okay, and knows about this network here that we're not going to use. But as far as its 10 networks, this is all it knows about. Okay, it just knows about this network here, 10.99.1.0. It does not know how to reach this network here, so it drops the packet. We're going to fix that with routing. Okay. All right. I do want to mention a little bit about this network here. Okay, this is one network here. We have 3 routers, all with an interface belonging to 10.99.1.0. Edge is 10.99.1.1, LAN 2 is 10.99.1.2, and LAN 2 is 10.99.10.3. See, they all have an interface on the same network. This is a switch, not a router. Okay. All right. Let's see. I think that's good for doing that right now. All right, the next thing I want to do, there's a couple more commands, verification commands in the lab, but I think we're good to go for right now. What I want to do now is what you've been waiting for, is let's configure OSPF on LAN 1, LAN 2, and Edge. And again, we're only going to configure it for the interfaces in this area here. So Edge will configure OSPF on this interface here to form neighbor relationships with LAN 1 and LAN 2, but not with the ISP router. Okay, we'll take care of that in a moment. Okay, so let me do this. I'm actually going to copy this in here to make it a little faster. So we're at LAN 1 here. I'm going to go into global configuration mode. I'm just going to paste some commands here, and let's see what I just got done pasting. Okay, router OSPF1. This is the process ID. Here's the router ID. Here's 3 network statements, one for each of its interfaces. And we talked about that in class. All right, so we've taken care of LAN 1. Let's go ahead and do LAN 2. Okay, I'm going to do LAN 2 slightly different. Okay, so let me copy that. Make it a little faster. Config T. I'm going to do paste. Now let's talk about what I'm doing here. Okay, again, router OSPF1 doesn't have to be the same process ID, but it makes sense. Best practice. Talk about that message in a moment. The router ID and one network command. Now, I don't recommend this as a best practice, but what we're doing here is we're saying, see this network address and mask, this wildcard mask. Okay, this is saying anything, any of my interfaces that belong to the 10 network. Okay, enable those for OSPF. Okay, join OSPF multicast addresses on that network and advertise those networks. Well, LAN 2 actually has 3 interfaces that belong to that network. Okay, it has this interface here, gig 00, that belongs to the 10.0.2.0 network. It has a 10.99.3.1 address that belongs to the 10.99.3.0 network, and has another interface that belongs to the 10.99.1.0 network with the .3 here. So just putting the 10 here with this wildcard mask, this is saying any of my interfaces that begin with 10, enable it for OSPF. Now, what happened here, as soon as I did that, we got these are OSPF adjacency messages. And it says, I've just formed an adjacency on 2 interfaces, gig 01 and gig 02. And with a neighbor, there's that neighbor, LAN 1. Now, LAN 2 formed a neighbor relationship with LAN 1 on this link here and this link here. two different networks. So they're connected to each other, maybe for redundancy, right? Two different ways, okay? But because they are both directly connected, although there's a switch here, that's fine. They're both connected on two shared networks. This is a shared network between them. This is a shared network between them. They both have interfaces on both those networks. They form neighbor relationships on both of those links or networks. Okay, we still need to do edge. I'm going to do edge even a third way. Okay, so let me copy it. Okay, then we go config T, paste. Okay, all I've done so far is done router OSPF1, and the way it pastes, it puts in an extra blank line there. But there's the router ID, and that's it. No network commands. Why is that? Because I'm actually going to go into the interface. I'll type this in. I'm going to go into interface gig 00. Okay, so it's only this interface I'm going to run OSPF on, not gig 02. And for this lab, not gig 01, just gig 00. And I can just do this. I can just say IP OSPF, get that out of the way, 1 process ID area 0. Okay, we should see some more adjacency commands coming up here in a moment. And also you'll notice that part of this, it says going from loading state to full state. There we go. So it just actually formed two neighbor relationships here, one with LAN 1, one with LAN 2, both on the same interface, gig 00, and it went from the loading to the full state. Okay. And actually, we should see that on the other routers as well. There it is, neighbor 33333, neighbor 33333. Okay, so you'll see these messages on both routers. Okay, let's see what these routers know. Let's go to, we're at LAN 1. Let me do end here. Okay, show IP route. Now, let's see, LAN 1 still knows about its directly connected networks, right? Okay. But look, it has learned about the 10.02.0 network. So this is LAN 1, has learned about this remote network, actually via two different sources, okay, or two different neighbors. It's actually the same neighbor, okay? But let's take a look. It's learned about it out its gigabit 01 interface right here with neighbor at 10.99.1.3 right here. So this was one that it learned about it from. And here's the other one out its gigabit 02 interface, which is right here. And with the neighbor at that IP address, next hop address, 10.99.3.1. Okay. Now these are equal cost paths. They're both a cost of 2. Even though there's a switch here, that makes no difference. Okay. It's still that each one of these gigabit interfaces has a cost of 1. So it's 1 plus 1 or 2, then 1. That's all 1 here. 1 plus 1 is 2. All right, we can do the same thing. Over here, we can see that LAN 2. Let me do an end here, show IP route. Okay, it has learned about LAN 1's local area network over here, 10.0.1.0, and the same thing, okay, via two different next hop addresses. All right, that's kind of cool. And what about edge? Show IP route. Okay, and it knows about 3 networks, 10.0.1.0, 10.0.2.0, and 10.99.3.0. Okay, so what edge has learned about is this remote network, this remote network, and this remote network, but 2 ways to this remote network, one via LAN 1 and one way via LAN 2, equal cost paths. Okay. All right. So it looks like we've got routing happening in here. That looks like it's working okay. We could even take a look at their adjacency tables. Show IP OSPF neighbor. We just do LAN 1 and I'll do edge as well. we can see LAN 1 has formed a relationship with 22222, 22222. Is that too many twos? Am I saying? But anyway, that's LAN 2. But again, via two different networks, it's done it through, or out two different interfaces. Okay, and it's also formed a neighbor relationship with edge. Okay, and these are the next hop IP addresses, or the other ends, the IP address of the neighbor. Okay, we'd see similar on LAN 2. I'm going to go down here to edge, show IP OSPF neighbor, and stretch that out a little bit better. There we go. And edge sees both LAN 1 and LAN 2 as its two neighbors. Okay. So this is one of the first commands we'd use in troubleshooting. Make sure we can see our neighbors. Okay, a couple of other commands I just want to go through briefly here. Show, let's do it from LAN 1, show IP OSPF. This is basic OSPF information. Okay, the routing process ID, router ID. There's that SPF information I talked about in the lecture. Where everything right now is in area 0, and it says how many interfaces does LAN 1 have in running right now just in area 0, but OSPF has 3 interfaces. All right, we can actually look at some other things as well. We could do show IP OSPF, but get specific interface information by saying interface and giving one of the interfaces like gigabit 01. That's this interface right here. So what kind of information does it give us? Well, some of the same information, process ID, router ID. One of the things that's interesting, network type broadcast, we will change that. No, we're going to leave that alone here. This needs to stay broadcast because we have more than 2 routers sharing this network here. Okay, I'm talking about this network right here, this interface here. So this needs to stay broadcast. Why is that? Well, one of the routers is going to act as a designated router. Actually, this router is the designated router. And there's a reason for that because it actually booted up first and there was nobody else booted, or I'm sorry, not to say booted. This router here was enabled first for OSPF, held the OSPF election, LAN 1 did. LAN 2 and edge weren't enabled yet for OSPF. So it says, okay, I'll be the designated router. Okay, so that's why it's the designated router. Okay, which isn't necessarily how you want things to happen. Yep. Anyway, we'll talk about that a little later. All right, so can PC0 now ping PC1? Let's take a look. Okay, so prior to us configuring routing OSPF here, it could not. But now all these routers, Edge, LAN 1, LAN 2, know about each other's remote networks in our OSPF routing domain. So we would expect that to work. Oh, what's going on? Is it not going to work? Oh no, what did Rick do? It works. You could probably tell I knew it was going to work. Okay, why did we get this request timeout? Well, it was not because the ARP request from PC0 getting needing the MAC address of its default gateway, because we already pinged that. But it was most likely because either LAN 1 needed the MAC address of LAN 2's Ethernet NIC card to encapsulate the packet, or LAN 2, or this also could have been both of these reasons. LAN 2 needed the MAC address of PC1 before it could encapsulate the packet in an Ethernet frame and send it to PC1. So yes, ARP process needs to take place because they all have ARP tables or ARP caches. All right. Can the edge router, let me get rid of that for a moment. Let's go to the edge router. Can it ping PC 10.0.1.50? And yes, we can see that's successful. Again, because all these routers know about each other's networks. But let's take a look at something here. What about ISP. Can the ISP router ping PC0? Let's try that again. This is not looking good. Okay. All right. So let's talk about what's happening here. Okay. So let's go through this, and we're going to see exactly what is transpiring. This is one of the wonderful things about networking and learning about networks, is understanding just the individual protocols and the things that happen step by step. You don't have to memorize scenarios. You can you can analyze any situation and hopefully troubleshoot it by just understanding the individual protocols. Okay, so let's take a look. Okay, so let's think about this. ISP, remember, has a route to the 10.0.0. Anything beginning with 10 sends to the edge router. So this packet did get from ISP to edge. All right, that's fine. So remember the destination IP address. Here's our destination IP address. Destination IP address is 10.0.150. That's our destination IP address. Does edge know how to get there? Okay, well, as we've seen previously, edge does know how to get to 10.0.150. Okay, it forwarded the packet to LAN 1. LAN 1 receives it. Oh, 10.150 is on my network, sends it. PC0 is now going to return a packet to the source of the ICMP echo request. The source of the ICMP echo request is 172.16.1.2, this interface on ISP. So what does PC0 do with packets that it's not in its own network? It sends it to its default gateway, 10.0.1.1. Okay, all right. So the packet went from PC0, the ICMP echo reply. So let me make a point here first. The ICMP echo request got there. So the packet did reach PC0. Okay, just because we see something like, go back to ISP here, just because we see this fail doesn't mean the packets didn't get there. It may mean that they got lost somewhere coming back. So the packet did get there. Now, PC0, we said, sends it to its default gateway, LAN 1. Let's take a look at LAN 1. Let's take a look at its routing table. Show IP route. Does LAN 1 have a path, a route to get it to 172.16.1.0 network? No. It only knows about its directly connected networks and about its internal, this network here, this internal remote network. Knows about nothing else. So this is where the packet got dropped. Okay, was the echo reply says, I don't know how to send it back, how to send it to 172.16.1.2, the source of the echo request, the destination of the echo reply. Oh, isn't this cool? Isn't this cool? Okay, so obviously we need a way for these routers, LAN 1, LAN 2, and even edge, to get to other networks outside what they know. Okay, because LAN 1 and LAN 2 only know about the 10 network. Edge only knows about the 10 network and its directly connected networks here. Okay, but edge doesn't know about the internet. We're going to fix that now. All right, so let's go to edge. And on the edge router, what we are going to do, like this, okay, going to go global configuration mode here. And what I'm going to do is I'm going to configure a static default route on edge. So this means This is the default. Nothing needs to match. And if it's not a specific match, a better match in my routing table, anything more than 0 bits, then I'm going to send it to the next hop router right here, which is the ISP. All right. Okay. Well, that helps edge. Okay. And matter of fact, if I do end here, do show IP route, we can see that edge now has the default route. Okay. But LAN 1, it still doesn't have a default route. Let me do show IP route again. It's still not in there. Okay. So what we have to do is in edge, we have to go into router OSPF. Let's do this. Router OSPF1. And we have to give the following command: default information originate. Okay. What this command does is it advertises that its default route, its static default route, to all of the routers in the OSPF domain. Say, hey, your way, if you don't know what to do with a packet, you don't have a better match, you now have a default route, and it's going to come eventually to me. Hey, let's take a look. Let me do the up arrow here, show IP route, and there it is. LAN 1 now has a default route. Let's go to LAN 2 here. Show IP route. There it is. Now as a default route. Okay. Of course, they are directly connected to edge, so they'll send them directly to edge. All right. Let's go back to our ISP. I think that's right there. Now let's try that same ping. And success. Ah, isn't this cool? Okay. Matter of fact, we could even do a trace route. Okay. Trace route 10.0.1.50. And we can see the path it takes. Went from ISP to edge, 172.16.1.1, and then to 10.99.1.2, 10.99.1.2, and then to the PC0. Ah, isn't this cool? All right. Hey, let's do this. Let me get rid of that here. Hey, we should have complete reachability now. The edge is sending everything to the ISP, which gets us to the internet, right? Okay. Does this mean PC0? See this over here, this web server 192.168.1.88. Let's see if PC0 can reach it. Yeah, let me make that a little lower. There we go. Oops. Okay. Ping 192.168.1.88. Let's see what happens here. Looks like we're going to have an ARP request here or there, but yes, the rest work. And if I did it again, no problem. Hey, let's do a trace route. Trace RT Windows 192.168.1.88. And we can see the path it takes. Okay, default gateway right here. Then 10.99.1.1. Where's that? That is edge. 10.99.1.1. And then 172.16.1.2. Here we are at the ISP. And then there we are at the Internet Web Server. Gosh, this is so cool. All right. Let's do something. So these routers all know about the 10 network. And if it's not one of their subnets, okay, for example, let's go to LAN 1 here. Okay, LAN 1 knows about all these 10 subnets, either directly connected or learn via OSPF. But remember, Moy Enterprises owns everything that belongs to 10 network, right? What happens if we sent a packet trace route? We'll do this from LAN 1. If I did a trace route to 10.55.55.55, something in the 10 network that does not exist, what would happen? Let's take a look. Uh-oh, what in the world has happened? I better do a Control-C here. Oh, Control Shift X. That's what Control Shift. Okay. Actually, the command is Control Shift 6. All right, but I didn't get there fast enough. But that's okay. Let's see what happened. It finally just stops. The trace route only goes so far. So LAN 1 sent it to Edge, okay, because it has a default route. Edge says, oh, 10, 55, 55, 55. Edge says, is that in my routing table? Okay, I don't have a 10, 55, 55, 55, but I do have a default route and I send it to the ISP. So it sent it to the ISP. The ISP says, that's nice. I'm sending it back. So when it goes to the ISP, okay, then the ISP sends it back to us. So it goes, and then we send it back to the ISP. And it's just, you can see that's just bouncing back to and from the ISP here. So we send it to the ISP sends it back to us, we send it to the ISP, we have a routing loop. So what do we have to do? One of Rick's favorite things he likes to tell students about. Okay, and oh, there we go, there's my LAN 1 there. All right, what we're going to do is on the Edge router, configure a discard route. So let's do that. Exit, global configuration mode, paste. There's my discard route. So I'm going to add a new static route. This time, anything for the 10 network, but anything that only matches the first 8 bits, send it to null 0. Let's do an end. I'm going to do a show IP route. So now we can see that there is this discard route. So if we have a better match for anything in the 10 network, like these /24s, for example, then hey, send them there. But if we have a packet that's for the 10 network and we don't know what to do with it because it only matches 8 bits, we're going to send it to the bit bucket. All right, let's try this at LAN 1 again in that same trace route, and we can see it gets dropped immediately by the Edge router. Wow, this is so cool. All right. Let's test a little redundancy here. Okay, so what I'm going to do here is from PC0, we're going to ping the internet web server. While we're doing that, I'm going to shut down this interface right here between LAN 1 and the Ethernet switch. Okay, but first let's do a trace route and let's verify that's the path it's currently taking. Okay, we've done that prior already. Actually, I'll just use this. We can see that went to LAN 1 here, its default gateway, and then from here to Edge. Okay, and then to the ISP. Okay, so what I'm going to do here is I'm just going to do a ping -and-1000 to 192.168.1.88. Okay, all right. While I'm doing that, let's go over to LAN. And I'm going to config T. Oops, I can see it's interface gigabit 0/1. And I'm going to do a shutdown. I'll watch the link light. Okay, now looks like we're not getting some pings for a second. Okay. There we go. It's okay. But we're getting some replies. Well, what's happening here? Oh, there had to do, it looks like I had to do an ARP request somewhere. Packet trace is a little strange sometimes. Okay. Okay, so let me kill this here. So what happened here, reason for the pause was, remember, the dead timer had to expire. Okay, so let me do a trace route here. Let's do another trace route. And this time, come on, packet tracer. You can do this. Come on, packet tracer. Okay, let's see, kind of strange there, packet tracer. There we go. That's a nice packet tracer. It's a little strange, but it's a great tool. Thank you, Dennis Fresno. Okay, so we can see what default gateway, but this time it went to 1099 3.1 down this way. And then, so then 1090 from LAN 2 to edge and then to the ISP. Okay, pretty cool, huh? All right. By the way, if we take a look at LAN 1, we can see the change went from full to down. This, okay. And it's telling us most likely because the interface is down or detached. All right. Matter of fact, let's stay on LAN 1 here. Let's do it. Look at the routing table. We can see it only has one path for the 1099 network. Okay, that's now no longer directly connected network. It used to be directly connected. Now it has to reach that network through LAN 2. Okay, let's see if I can move up here if I see it. Remember the 1099.1 network used to be directly connected until we shut it down. Now it still has a connection to this network, but via LAN 2. Okay, this is so cool, this stuff. All right, let me do this. Let's go to config T here. Interface, let's bring it back up. I'll just do a no shutdown here. Okay, see it went green automatically on the switch? That's because I did that spanning tree command port fast. All right, just a couple more things and we're almost there. Okay, so the next thing we're gonna do is just configure LAN 1 and LAN 2 for passive interfaces under two LANs. They have no neighbors out these interfaces. So there's no reason for these routers. And here, we're going to do show IP OSPF interface gigabit 00. What I'm showing you here is on this interface, it's sending out hellos every 10 seconds. There's no reason to do that because there's no routers out there. Okay, and if we put a router out there, then that'll be different. But they just don't appear. Okay. All right. So what I'm going to do here is config T router OSPF. How do you spell OSPF? OSPF1. Then I'm going to say passive, hit the tab key, passive interface gigabit 00. Okay. And I'm going to do the same thing on LAN 2. Config T interface gigabit 00 for its network, its LAN interface with no routers. Passive. Oops, what am I doing? No, wrong thing. Sorry. I'm thinking interface gigabit 00. See, I was trying to do the passive command. That's not going to work on there. I got to go router. I like it when Rick is fumbling, right? It's good. It's good. All right. Passive interface gigabit 00. Think about this business. We all help each other. Just gotta leave the egos at the door. All right. So passive interfaces on both those interfaces. Okay. Let's do an end here. I'm going to do show IP. Just do the up arrow again. Okay. So if you notice, we'll take a look here that it's still, looks like it's let's see, still has the timer intervals. This is what I want to show you, but no hellos because it's a passive interface. Okay. Also, if I can see where I have passive interfaces, when I do show IP protocols. Okay, it tells me I'm running OSPF. Shows me that I'm running OSPF, but also tells me what my passive interfaces are. Okay, good stuff. Okay, another thing we want to do here, and we're getting close to the end. We're almost there. Between LAN 1 and LAN 2, okay, it has an Ethernet network, but it's a point-to-point link. There's only the two of them. Unlike this connection where there's 3 routers, where you need to have a DR and BDR. Here you do not. There's only the 2 of them. So let's do this. On LAN 1, what I'm going to do is go in config T. I'm going to say go interface. Let's see, does anything I want to show you? Let me do this real quick. Show IP OSPF interface. Yes, I do want to show you this. Interface gigabit 01. I want you to notice right now it's set as a broadcast network. Okay, that's this interface here where you have the switch. And that's what we want. We want to keep that as a broadcast. But let's look at its gigabit 02 link, the point-to-point link. Up arrow, put a 2 there. It's also network type broadcast. This we want to make just point-to-point. All right, so this is what I'm going to do. I'm going to say config T, interface gigabit 02. I'm going to say IP. This we configure on the interface, IP OSPF network. And if I hit question mark here, gives me just this one option in packet tracer, point to point. Okay, now the adjacency's gone down. Okay, and then it's going to come back up. But I want to do the same thing on LAN 2. Okay, I'm going to do exit, interface gigabit 0/2. Okay, and again, IP OSPF network, point to point, brings down the interface, brings it back up. But let's take a look at that command. Show IP OSPF interface now. You'll notice now the network type is point to point. There is no DR. Okay. Prior to this, it was network type broadcast, and there was a DR and a BDR. One was the DR, one was the BDR. It's like there's two people that live in your country. One gets to be president, the other one gets to be vice president. That's it. There's only the 2 of you. Okay. But now you say, we don't need that. There's only the 2 of us. Okay. Point to point, there's no DR or BDR. Very cool stuff. Very cool stuff. All right, I would like to show you one final thing, okay? I'm not going to have you configure, although it's part of the lab if you wish to do it, the DR, BDR. There's one thing I think is important to go through, and that is to see what happens when you modify a hello interval, okay? Show IP OSPF neighbor, okay? So LAN 1 and LAN 2 are neighbors on their gigabit 02 interface, okay, right here, okay? And there's no DR, BDR like the other interfaces, okay? All right, so we are neighbors, okay? But what happens, and let me do one other thing here. We're going to do show IP OSPF gigabit 02 again. We do have hello and dead intervals. Okay, this is LAN 1. I do LAN 2, by the way, and show IP OSPF interface gigabit 02. Yes, we have matching hello and dead intervals. Okay, we match on our gig 02 interfaces. Now what I am going to do is change it on LAN 1. Okay, I'm going to say interface gigabit 02. I'm going to say IP OSPF hello interval, and I'm going to change that to 30 seconds. in 30 seconds. Okay, now OSPF will, on Cisco routers, will automatically change the dead interval to 4 times the hello interval, but Packet Tracer does not. So what I'm going to do is also change the dead interval to 4 times. Dead interval, 120. Okay. All right. Now, what do we expect to happen here? We've changed the hello interval on dead interval on one side, but we did not change it on the other. Okay. So what we expect to happen is that adjacency to go down. It will go down after the dead time expires. Now you can see it's already expired at 40 seconds on LAN 2. Now, after 120 seconds, it expired on LAN 1. They lose their adjacency. Matter of fact, let's just do it here, show IP OSPF neighbor. Although we do have a neighbor, LAN 2 has a neighbor adjacency with LAN 1, but it's via that other network, 1099 1.2 network, 1.0 network, this network here, not here. Okay. All right. If I want them to be neighbors, I've got to make sure that their hello intervals are the same. Okay. So I can change, I have a choice. I can change one of them back. Well, let's do this here. Show IP OSPF interface gigabit 02. Let's verify that, yes, we did change the hello and dead intervals. Okay. So let's just change it on LAN 2 as well. Okay, that's kind of a long hello interval, by the way. But for the lab, it's okay. Okay, IP OSPF hello interval, we said 30. And IP OSPF dead interval, 120. Okay. So in a moment here, we should see that they are going to both reach an adjacency. Of course, they're now going to send them every 30 seconds. So Rick is going to have to talk a bit. But after 30 seconds, they should see each other's hellos and then form the adjacency and then go from, the init state, the down state to init state, to two-way state, to start, to exchange, to loading, to full. And there we are. Loading to full. Wow, how did Rick remember that stuff? You would remember things too if you talked about them for year after year. All right, let's make sure that we see the neighbors, that we see each other as neighbors. I'll do exit again. Okay, and yes, I see you as a neighbor on that link, on my gig 02 link, where we have the point-to-point link. All right. I am not going to have you do this, but you can if you wish. In a multi-access network, it's a good idea to modify the designated router. Okay. So you want to determine who the designated router is. Now, it just so happened that if one router boots up first and the other ones are still booting, or you add them later, well, you hold an election where there's no competitors. Yes, you're going to be the president, or you're going to be the designated router in this case. If there's already a designated router and another router joins, says, oh, there's a president. Who wants to be vice president? If there's no other routers, you're the vice president or the BDR. What the lab here is showing you is first how to clear those processes. Okay, and you kind of get the commands all ready to go and hit enter on each one. There's better ways to do this in a production network, but here we're forcing the election process. Here, if we wanted LAN 1 to be the designated router, we give it a higher priority on that interface. So what we're talking about here is this network here and each of their interfaces. Okay, whoever has the highest priority on that interface becomes the designated router. By default, they all have a priority of 1. So it defaults to the highest router ID, or in our case, if who's ever there. Okay, so anyway, I don't think it's necessary to go through all this, but you can see it. All right, so I do have the final running configs too, to show you what your running configs may look like, or some of the configurations. Okay, again, what you will submit is everything up to. So if you do decide to do the modifying the DR, save your running configs as they are now. This is what you'll be submitting. Okay, so these, save your running configs. Again, copy run to start. So what you will do on each router. Copy run to start. It's a good idea to be doing this as you're doing the lab. And even the ISP, let's do them all. Okay. Okay. Once we've done that, save your packet tracer file. File, save as. Okay. Not startup, we'll call it Rick. Okay, and I'll save it to my OSPF directory. Okay. Now, depending upon what you are required for with the lab, okay, and you have to look at the lab instructions because I change this from time to time. Okay, typically you'll be submitting 1 or more running configs, sometimes some outputs as well. All right, so please check with the lab document what is required, but you're all set. We've done it. We've got everything working. All right. And again, the important thing with all of this is really to understand what is transpiring. When you do something, what do you expect to happen? What else do you need to do to make other things happen? Okay. When there's a failure in the network, okay, you should understand what's going to transpire after that failure. Okay. Or if there's a problem, where is the failure point? That's what I loved about that first troubleshooting exercise we did, where the echo request from ISP reached PC0, okay, and got from PC0 to LAN 1, but LAN 1 did not know about this destination network, or specifically this destination IP address, but did not have in its routing table this destination network, so it dropped the packet. Okay, so failure or not being able to communicate doesn't mean that a packet doesn't get there. It may be an issue with the return path. And this, again, is all you need to understand is be able to follow a packet and understand the processes. Just don't assume things happen by magic. Look at the routing tables. Think about what is the destination IP address. What does the device or the router know? What doesn't it know? What is missing? What should be there? What do you need to add? In this case, we added a default route that we then advertise using default information originate to the rest of the OSPF domain. So they now knew how to to forward packets that it didn't know about, like this network here, then one knew to forward that to edge. And to make it even better, we configured a discard route. So any packets that belong to the 10 network here, the 10.0.0.0/8 network, that there was not a valid path for in any of the routing tables, weren't just sent to edge and ping-ponged between edge and ISP. We configured the discard route for it to drop those less specific matches. All right, great job, everybody. Hope you're enjoying this lab. It's very cool that it's not just about the configurations. You know, just got done talking to Russ White, my buddy Russ, that I talk a lot about, well-known network analyst, network engineer throughout the industry, well-known author, presenter. And we were just talking about yesterday how the configurations are easy. What's important is to understand what is taking place. So you know the effects of your implementation, starting with your design, your effects of your implementation, and how to troubleshoot. Good job, everybody.